Hi again and welcome back to maths class. So today what we're going to look at is differentiating trigonometric functions, and what we looked at in the previous video was we looked at what is the derivative of sine and cosine, and what we're going to look at today is the tan function as well. But before we do that, I want to have a quick summary of where we're up to, because basically we now know all the basic derivative rules that we need to know. So I just want to quickly run through what those are. The first one is our rule that we use for polynomials and for power functions, where if my function is x to the power of n, then I multiply by n and I subtract 1 from that power to find the derivative. For my exponential function, e to the kx, I multiply by that constant k, and then the rest just stays the same. This is a beautiful one, so easy. E to the power of kx, it's its own derivative, but I just get this extra constant. The logarithmic function, e to the log base e of ax plus b, so in other words, I have a linear function in the argument. I end up with, on my numerator, I have the coefficient of that linear function, coefficient of x, that's a, over the linear function itself, ax plus b. And if I generalize that even further, log base e of f of x gives me f dash of x over f of x. Now, it's a really good idea to have a summary sheet like this, because once we start using the chain rule more and some other rules, we're going to use combinations of all of these, and it's good to have a handy reference somewhere where you've got them all written down. So what I've got here then is a summary. I've added to my summary, the derivative of sine of kx is k cosine of kx. The derivative of cosine of kx is negative, remember the negative, k sine of kx. So to help me remember that, we always change between sine and cosine when we're finding the derivative, and cosine goes to negative, okay? And always remember also to bring that coefficient out the front. And finally, we haven't yet looked at tan x, and I'm going to talk a little bit about, where is it? Lost my little sheet. Hang on. Oh, I'll just pause while I look for it. Found it. So what we've got here is a quick little summary sheet that helps us to look at some notation before I go ahead and talk about the derivative of the tan function. So when we have composite functions involving trig functions, for example, if I have sine x and I square that whole thing, we actually write it like this, sine squared x, and that's to ensure there's no confusion, because sometimes people might write sine x squared and it's not really clear. Is that sine of x squared, or is it sine x all squared? So we don't use either of those notations. We use this, and now it's really clear that it's sine x all squared, okay? Same for cosine x. If I want to square all of cosine x, I write it like this. The problem is this notation is limited because this doesn't mean 1 over cosine x. It already means something else. It means the inverse of cosine. We use this, if you remember, when we're looking for the angle, all right? Similarly, this means inverse sine. So I can't use these to represent 1 on cos x and 1 on sine x. So we actually have separate names. 1 on cos x is called sec x, and although we won't use this one, 1 on sine x is called cosec x. Now, the reason you need to know that is because the derivative of tan kx is k times sec squared kx. So sec of x is 1 on cos x, all right? Therefore, this is equal to k over cos squared kx. So now I'm just going to do some examples, and I'm going to refer back to this sheet to help me. My first example, I'm going to differentiate y equals -4 times cosine 1 minus 2x. Now this looks to me like a composite function because I have this inside function here. So I'm first going to define u as 1 minus 2x, and then y I'm going to rewrite in terms of u, -4 times 1, sorry, negative 4 cos u. Okay, so now I find dy du. Let's go back to my rule list. If I've got cos u, what's the derivative? The derivative of cos kx is negative sine kx. Well, there's no k involved. So the derivative of cosine is negative sine. So this is going to be negative 4 times negative sine u. And du dx is going to be negative 2. Okay, so dy dx is going to be dy du times du dx. So my negative 4 times the negative is going to give me positive 4, but then times negative 2 is going to give me negative 8 sine, and instead of u, I'm going to write 1 minus 2x. Okay, second example. I'm going to differentiate f of x equals sine squared x. This is going to be this is another composite function. I need the chain rule again. There's two things I need to do then. Because this is in f of x notation and I want to use my dy dx notation, I must write let y equals sine squared x, because I can't just introduce y without defining what it is. Then I'm also going to say let u equal, now what's the inside function here? Let's think about it. If I put a value into x, what would I do here? First I would go sine x, then I would square it. So sine x is the inside function. So in fact, if I rewrite this as sine x squared like that, which I won't normally, but just to help me get the idea that yes, sine x is the inside function and x squared is the outside function. So u equals sine x. In that case, y equals u squared. Now I just have to differentiate y with respect to u and u with respect to x. dy du is 2u. du dx is, let's go back to my list. I'm differentiating sine x. The derivative of sine kx is k cos kx. So the derivative of sine is cos. So that's just straightforward cos x. I don't make it negative or anything like that. dy dx is what I want now. It's going to be dy du times du dx. But I don't want to keep u. I want to replace u now with sine x. So that's going to be 2 times u, which is sine x, times cos x. And I'm going to put my little multiplication points in there just to make it really clear. I'm multiplying 2 times sine x times cos x. And that's the answer. 2 more examples. For my next example, I'm going to differentiate y equals cosine of the log base e of x. This is clearly a composite function. My inside function is log base e of x. My outside function is cos x. So first I'm going to define u as log base e of x. And then I write y in terms of u. Y is now cos, not log base e of x, cos u. I differentiate both of those. dy dx equals the derivative of cos u. Now remember, cosine becomes negative sine u. And du dx, can you remember? Log base e of ax plus b is a over ax plus b. Now in this case I don't have a plus b. I've just got x. So it's going to be a is 1 over x. Okay. Sorry, I've written dy dx here. That should say dy du. Right there, because that is I've differentiated y with respect to u. Now I want dy dx. It's going to be dy du times du dx. Negative sine, but instead of u, I'm going to replace it with log base e of x so that my final expression has no u's in it, only x's, times 1 on x. I'm just going to write that as over x. And I'm done. I can't simplify that. I'm not even going to try. My last example is not too tricky, but it does involve the tan function. So I'm going to differentiate the tan function. This is not a chain rule. I've got tan of 5x, that's just x with a coefficient. Let's go and look at my rule. Tan of kx is k times sec squared kx. So dy dx is going to be k out the front, and then sec squared of kx, sec squared of 5x, and I wrote k when I should have written 5. Dy dx equals 5 times sec squared 5x, or I can write that as 5 over cos squared 5x. All right, that is the how-to of differentiating circular functions.